All right, welcome to the NASA Connect studio. Now joining me in the studio are Rich Silcox, a senior research scientist, and we're also now joined by Dennis Huff from NASA Glenn Research Center in Cleveland, Ohio. But before we talk to our researchers, let's give you a chance to do some analyzing using the data from the experiment you just saw. After this segment, our two researchers will be answering your email questions and taking questions from the viewing audience. Okay, now, look carefully at the data and using the information in the following diagram, work with your fellow students to answer the questions as read aloud by Rich Silcox.
As the distance increased from 50 meters, what happened to the mean time? Use the formula percent of experimental error equals calculated value minus accepted value divided by the accepted value times 100 to calculate the percentage of error at 50 meters and 300 meters. Why do you think they are different? The speed of sound is directly proportional to air temperature. Is the speed of sound faster in the summer or winter? Why?
We're back, and with me are Rich Silcox and Dennis Huff to answer your questions. But let's start things off by asking Dennis, what is it, Dennis, that you actually do there at NASA Glenn?
I'd be glad to answer that. Hello, my name is Dennis Huff. I'm the chief of the acoustics branch at NASA's Glenn Research Center that's located in Cleveland, Ohio. Our contribution to quieting the skies looks at ways to making the engines quieter. Our goal is to develop engine noise reduction technology without compromising the engine performance or the aircraft safety. Some members of our team develop mathematical models to be able to predict the sound from the engine, while others test different parts of the engine inside wind tunnels and anechoic chambers. Our best noise reduction concepts will eventually be tested on engines to make sure that we can really make the airplanes quieter.
You got a lot of good stuff going there that I could ask a lot of questions about, and I just might do that, Dennis, but I've got some email questions that have come in for both of you guys. So let me start with an email question. The first question is, does the shape of a plane affect the sound? And this is from Jonathan in Virginia Beach.
Yeah, Shelley, the shape of the airplane does change the sound dramatically. For instance, when the airplane is coming in for a landing or taking off, the flaps in the landing gear are deployed. In that case, the flow is very dirty and it makes a lot more noise than when those components are stowed away.
Okay. Yes, and in fact, it's interesting on the engine itself. You'll notice that some of the older aircraft have smaller diameter engines. And the smaller diameter actually passes a lot more flow at a higher velocity, and this causes the jet noise to be very loud. We have a general rule of thumb that we say that the velocity of the exit of the velocity raised to the 8th power is proportional to the jet noise. So the newer aircraft that have larger diameter engines actually end up being quieter.
All right, and let's go back to this. You've probably kind of answered this already, but I'm thinking about me, who flies an awful lot on these small little, they call them puddle jumpers or commuter planes, compared to your bigger 757s. How is there a difference on those size of engines and the noise that they are generating?
Sure, those engines are some of the newer engines. We call those higher bypass ratio engines. And so you got a lot of flow going through that. It's a lot of thrust in that engine, but it's going at a lower velocity, so it's a much quieter engine than the older ones.
Oh, okay.
In a lot of cases, the propeller airplanes are quieter, too. They're quieter than the large jets are.
All right, I got a question. You keep talking about research to reduce noise around communities. What is the community that you all are referring to here?
Well, generally, we're talking about that area around the airport that's affected by the operations of the airplanes taking off and landings. Once the airplane climbs to altitude, and is at cruise altitude, maybe at 35,000 feet, you don't really hear it much anymore.
Okay.
So,
all right, good. Well, I've got someone tell me we've got a caller out there, so let's go ahead and take that caller. Caller, could I have your first name, please, and your question?
My name is Timothy, and my question is, how fast is the sound travel through water?
Oh, okay. The sound traveling through water. And is there a difference between the speed that sound travels in air and water?
yes, the speed travels through water much more quickly than it does in air. I can't recall the exact number. I think it's 3 or 4 times faster in water than it is in air.
Okay. All right, so we know that it is going to travel faster through water than in air. Good question there, Timothy. I'm going to take a final question I have here by email very quickly. Well, no, final advice. What advice would you, Dennis, give to viewers about thinking about careers?
Be glad to answer that. My father gave me the advice to keep your options open. You can get into a lot of different activities and make sure you involve yourself in extracurricular activities, but also stay with your math and science and your English. All the different courses are very important.
All right, there you've heard it from us, and I see we're quickly running out of time. Thank you, Dennis and Rich. And now, students from Jonas Clark Middle School in Lexington, Massachusetts share some technology notes that are sure to sharpen your investigation on sound following this program.
One part of the website is called the NASA Sound Machine. With it, you'll learn about the shapes and characteristics of sound waves, how an airplane produces different kinds of noise, and what certain words would sound like if you had severe or partial hearing loss.
Another part of the NASA Connect website features NASA researchers talking about their jobs. It's called Career Corner. There's also a fun quiz that will test your knowledge of sound and hearing.